Superconductivity is one of the most exciting phenomena in physics because of the very nature of the phenomenon and also of its prospective applications of immense potential. Dear students, today I am going to discuss about this topic as a part of the course of physics majored in undergraduate course of Dibrugarh University. Content of my topic are what is superconductivity, electrical and magnetic properties of superconductors, effect of magnetic field and critical field, the Meissner effect, type 1 and type 2 superconductors, high temperature superconductors. We know that the electrical resistance of a metallic conductor decreases gradually as temperature is lowered. In ordinary conductors such as copper or silver, this decrease is limited by impurities and other defects. Even near absolute zero, a real sample of a normal conductor shows some resistance. In a superconductor, the resistance drops abruptly to zero when the material is cooled near to 0 Kelvin. First, let us know the history of its discovery. It was the Dutch physicist Camerlingh Ons who discovered phenomenon of superconductivity. He was a professor of physics at Leiden University in Western Netherlands. He made cryogenic laboratory of the Leiden University to become the cold research center of the world of his time. His interest was in liquefying gases, the attempt which he succeeded in 1908. As an extension of his low temperature work, while studying the temperature dependence of resistance of metals, in 1911, Camerlingh Ons discovered that the electrical resistance of mercury dropped suddenly to about a millionth of its original value at very low temperature, 4.2 Kelvin, the melting point of helium. And below this temperature, mercury shows no resistance at all. He also later observed this property in lead and some other metals also. In 1913, he received the Nobel Prize for his work. Now, what is superconductivity? The phenomenon in which the electrical resistivity suddenly drops to zero when the material is cooled to a sufficiently low temperature is called superconductivity, and the materials in this state are called a superconductor. The temperature at which the resistance of a material suddenly falls to zero is called critical temperature or transition temperature and is represented by T suffix C. At this temperature, the material undergoes a phase transition from normal state to superconducting state. The good conductors like copper, sodium, gold, etc. do not show superconductivity. That is, free electron materials do not show superconductivity. But the poor conductors show superconductivity, like mercury, we show superconductivity at 4.2 Kelvin, niobium, tin, lead, etc. are the examples of some superconductors. This table shows some superconductors which their critical temperatures. Some characteristic properties of superconductors are zero electrical resistivity. Superconductors exhibit no electrical resistance. The resistance of a superconductor suddenly drops to an extremely small value near the transition temperature. The second hallmark of superconductors, other than its zero resistance, was perfect diamagnetism. Superconductor exhibits perfect diamagnetism or flux exclusion. Strong magnetic field causes the destruction of the superconductivity. On application of a sufficiently strong magnetic field to superconductors causes the destruction of their superconductivity. Persistent current. If an electric current is set up in a perfect superconductor, it can persist for a very long time without any applied EMF. If a ring of superconducting material is cooled in a magnetic field from a temperature to a value below critical temperature, and then magnetic field is removed, an induced current is set up due to electromagnetic induction. When the field is switched off, the magnetic field outside the ring disappears, but the flux inside the entire ring is trapped. It is observed that the induced current continues to persist with undiminished strength for indefinite period. Such current is called the persistent current. Persistent current is one of the most important properties of a superconductor. Now we see the effect of magnetic field. I have already said that it is possible to destroy the superconductivity of a superconducting material by the application of intense magnetic field. If a superconductor is placed in a sufficiently strong magnetic field, the superconductor becomes a normal conductor. That is, it regains its resistance. The value of magnetic field at which superconductivity is destroyed is called the critical magnetic field. The critical magnetic field is found to be function of temperature. The plots of variation of critical field versus temperature for different materials is found approximately parabolic and can be expressed by the equation as given as Hc equal to H naught 1 minus square of the T by Tc. Here H naught is the critical field at 0 Kelvin and Tc is the transition temperature of the specimen. It is seen that lower the temperature, the higher the value of Hc, and highest the critical temperature when there is no magnetic field, that is for Hc equal to 0, T equal to Tc. The curve may be viewed as a phase diagram, below which superconductivity is present and outside it the superconductivity behaves as a normal conductor. The superconducting property of the sample will be destroyed by magnetic field produced by the current through itself also. So there is a maximum value of current that can go through a superconductor. This maximum current is known as critical current density. If the current exceeds this value, the material becomes a normal metal again. The Meissner effect. The important property of superconductors, other than its zero resistance, is perfect diamagnetism, which was discovered by Meissner and Oxenfeld in 1933. They found the magnetic field is pushed out of the superconducting material no matter how this field is created by an external magnet or by passing a current through the material itself. This means that the magnetic induction inside the superconductor is always zero as long as it is in the superconducting state. Therefore, we can say the Meissner effect states that if a superconductor is cooled in a magnetic field from a temperature above transition temperature to below transition temperature, then at the transition temperature the lines of magnetic flux are pushed out of the specimen, which is shown in the figure, and this is known as flux exclusion. On the other hand, if the superconductor is initially cooled below transition temperature and then placed in the magnetic field, the flux does not penetrate the material. This means the superconductor behaves as diamagnetic. In both cases, Meissner effect is reversible phenomena. That is, as soon as the magnetic field is removed, the superconductor resumes its normal state. If a perfect conductor is first cooled from higher temperature to 0 Kelvin so that its resistivity becomes 0 and then a magnetic field is applied, no field enters to the perfect conductor. As soon as the field is removed, it becomes to its initial state. That means, like superconductor, flux exclusion is observed for perfect conductor in this case. But if magnetic field is first applied to the perfect conductor and then it is cooled until its resistance becomes 0, the magnetic field in the material gets frozen and cannot change subsequently irrespective of the applied field. This is in contradiction to the Meissner effect. Thus, we conclude that the behavior of superconductor is different from that of perfect conductor. Next, types of superconductors. First, type 1 superconductor. The superconductors which strictly follow the Meissner effect are called type 1 or soft superconductor. These superconductors exhibit perfect diamagnetism below a critical field. The typical magnetic behavior of a type 1 superconductor is shown in the figure. As the applied magnetic field is increased, the material loses superconductivity abruptly at the critical field HC, and diamagnetism suddenly drops down to zero. That is, the magnetic field penetrates the material completely. Above the critical field, the material behaves as a normal conductor. Type 1 superconductor are also known as soft superconductor because of their tendency to give away superconducting phase at low magnetic fields. The value of critical magnetic field is too small for soft superconductor, and hence these do not have any useful technical application. Type 2 superconductor. Type 2 superconductor do not follow Meissner effect strictly. That is, magnetic field does not penetrate these materials abruptly at the critical field. As shown in figure, the magnetic behavior of such a superconductor. For applied magnetic field below HC1, the specimen is diamagnetic, and hence the magnetic flux is completely excluded in this range of field. Thus, for magnetic field below HC1, the material exists in the superconducting state. The HC1 is called the lower critical field. As the field exceeds the lower critical field, the flux begins to penetrate the specimen, and for magnetic field which is equal to HC2, the complete penetration occurs and the material becomes a normal conductor. This HC2 is called upper critical field. In the region between lower critical field and upper critical field, the diamagnetic behavior of the material finishes gradually. The specimen in this region is said to be existing in the vortex or intermediate state. When the magnetic field is stronger, they prefer to adopt a compromised situation and allow some of the magnetic field in a cluster of flux to penetrate the material. In this case, screening currents circulate around each flux bundle like small vortices. The center of each vortex is normal, whereas the region of 0 to low magnetic field is superconducting. Thus, in this region, the specimen is in a phase which is mixture of superconducting and normal state. This state is called as vortex or intermediate state. Since in this type of superconductor, the magnetization vanishes gradually as the field is increased, and they do not lose the superconducting state by external magnetic field, or they can bear strong magnetic fields. Therefore, they are also known as hard superconductors. Type 2 superconductors are technically very useful material and can be used to manufacture superconducting wires. Here some examples of type 2 superconductors: niobium nitride, some cuprate whose lower critical field is 0.01 Tesla, but the upper critical field is 60 Tesla. Next, high temperature superconductors. Superconductivity is basically a low temperature phenomenon, but in the year 1986, a new class of superconductors based on rare earth oxide having a critical temperature above the melting point of liquid nitrogen have been discovered. This class of superconductors, whose critical temperature is comparatively high, are called high temperature superconductors. In 1988, several other non-rare earth based copper oxide was discovered, which showed superconductivity between 60 Kelvin and 125 Kelvin. Thus, the materials that behaves as superconductors at a temperature above 30 K, which can be maintained by using the simplest coolant liquid nitrogen, whose freezing point is minus 210 degrees centigrade and the boiling point is minus 196 degrees centigrade, are the high temperature superconductors. High temperature superconductors are some sort of rare earth element and some non-rare earth based copper oxide elements like lanthanum barium copper oxide, whose critical temperature is 30 Kelvin, and yttrium barium copper oxide, whose critical temperature is 77 Kelvin. I want to mention some applications of superconductors. The superconducting magnets have been used in NMR spectrometer. That means NMR means nuclear magnetic resonance spectrometer, which is widely used in research and development for sample analysis. The SQUID superconducting quantum interface devices fabricated using superconductors find application in medical diagnosis and undersea communication, etc. Superconductors have been used to produce electromagnetic shields and magnetic levitating planes. The superconducting wires will be used for power transmission or communication system without any loss. As an introductory lecture on the superconductivity, I conclude here. If any queries, you can write in the comment box. Thank you. Here there is a video on magnetic levitation. Here they use the superconductor yttrium barium copper oxide, whose critical temperature is 77 Kelvin. On the top of the superconductor, a permanent magnet is placed and liquid nitrogen is poured to the superconductor and allowed to cool down. When the superconductor is sufficiently cooled down, that means when it attains its critical temperature, it becomes superconductor, and then magnetic levitation will take place. Thank you.